Good afternoon, everyone. It's a pleasure to welcome today. Our speaker is Maria Celeste Artale. She's an assistant professor at Universidad Andrés Bello in Chile. She's a theoretical astrophysicist from Argentina, specializing in hydrodynamical cosmological simulations to study galaxy formation, cosmology, and gravitational wave astronomy. She got her PhD in 2015 from the University of Buenos Aires, and he has a postdoctoral position in Australia and Italy. She is currently a member of the Einstein Telescope Observation Science Board. Thank you for accepting the invitation.
Thanks a lot. Hope you can hear me well from the full room. Okay. Well, first of all, thank you very much for this invitation and for giving me this opportunity to talk about my research. And of course, for doing my research, I don't do this alone, and I included here a list of the list of my collaborators, but it's not complete, to be honest. But yeah, thanks also to all of them. I will talk about, as I said to Lars, a potpourri of what I was doing lately, and mostly focus on what is doing my new group in Andrés Bello, at the Universidad Andrés Bello. So, because of some historical context, my research is based on cosmological hydrodynamical simulations, but I use this tool to explore different open questions in astrophysics. And the three main topics in which I work on lately and now is on galaxy formation and evolution, in cosmology and large-scale structure, and also galaxy dark matter halo connection, but also on gravitational wave astrophysics. Yeah, I know the pointer is hard. So gravitational wave astrophysics, and yeah, and I will show you today how we can implement this tool, the cosmological hydrodynamical simulations, to study these three fields. I think that more or less you are, I guess, familiar with what a cosmological hydrodynamical simulation is. I will refer to, so what I am doing, what I am using now are large boxes, and that includes dark matter and baryons. And with baryons I include stars and gas, especially, and yeah, I was using Illustris TNG, Eagle, Flamingo. Lately I will show you some results using Flamingo. But yeah, these are my tools. So I can retrieve information about the galaxies, the dark matter halos, and the particle information. And I use this, again, as a tool in my research. So the outline of my talk, I decided to focus more on some aspects of gravitational wave astrophysics and some aspects on galaxy formation and evolution, but especially about high redshift. So in the case of gravitational wave astrophysics, I will focus on how we can use cosmological simulations to study the host galaxies of binary compact object mergers and the link with potential progenitors, which are high mass X-ray binaries. And for the case of the galaxy formation and evolution, I will discuss briefly about how we can study protocluster structures at high redshift, and how we can use different galaxy tracers for protocluster galaxy tracers that are Lyman-alpha emitters and submillimeter galaxies. And I will mention also, because what we are doing is in the context of a big collaboration of people, which the name is Auditório. So let's start with gravitational wave astrophysics. So gravitational waves are like perturbations, right, in ripples in space-time. And the sources for these gravitational wave events can be very large, is varied, right? But the point is that today I would like to focus on this aspect in particular. So I am working more on this range in frequency for the gravitational wave events. But what I'm going to talk today is more in this context of the terrestrial interferometers, like LIGO, Virgo, and CAGRA interferometers, and also the future, which is the Einstein telescope that in which I'm part of now. And these kind of interferometers can detect binary compact object mergers, which means black hole, black hole, black hole neutron star, or binary neutron star mergers. This is now, I would say, outdated, but is at least for now is the latest catalog that we have for binary compact object mergers. What you see here is it's a list of I mean, they are gradually distributed in mass. So you see the low mass here, and they are gradually distributed to the right. The blue points here represent the detections of black holes, and if you see, there are 2 points here in each one. So these are the 2 black holes that merge to this result, and you see this for all these blue points. So all these are from the third observational run. Now we have the fourth one still running, but in particular also and this one, sorry, are for binary neutron stars. The ones that you see here on the bottom are the masses of the neutron stars from electromagnetic detections, which means, for instance, pulsars, binary pulsars. And the ones here, the red points belong to black holes from X-ray binaries. At the beginning, the problem was, now you see it's a little bit different, but at the beginning, one of the big problems were that for the gravitational wave events, the black holes detected are very massive with respect to the masses of the black holes that we can detect from X-ray binaries. Now, well, we started to complement this, but there is still a big question between the black hole masses that we detect with from gravitational wave events with respect to the black holes that we can detect from, for instance, X-ray binaries. But yeah, also with Gaia, as you have heard, we can detect black holes binary system with black holes. So the idea is the following: we have a lot of binary stars that at some point, after some what we call delay time between the formation of the system and the gravitational wave happen. And the point is that in principle, each one of these events might be the product of a different environment, different formation channel. So nowadays we talk about these formation channels for the binary compact objects that we can detect with a LIGO, Virgo, CAGRA. We can split especially in 2 fields, in 2 main formation channels, sorry. One is in the field, which are like in isolation, like systems that are formed in a region where that is forming stars, but they are initially formed in binary systems. While in the case of the dynamical systems, are systems that are in dense sterile environments, like globular clusters or young star cluster or nuclear star clusters. And suddenly, due to 3-body encounters, they end in binary systems that eventually end their life as a merger of binary compact objects. But there are other possible sources, like primordial black holes and flybys, etc. Okay, so still what does, okay, I'm talking about gravitational waves, but now the question is what I'm doing exactly. What I do is, okay, do this of studying the possible formation scenarios and what are the properties of the host galaxies where these binary compact object mergers happen, where is more likely to find them. So, so studying exactly that, the host galaxy from the host galaxy perspective, it is very useful to investigate which are the most likely formation channels. So, because of course, star forming or quench galaxies will have different stellar populations. Also, if we have galaxies with that are metal poor or metal rich, we expect that the masses of our black holes might be statistically different. Also, if we have galaxies with AGN, active AGN, of course, or no AGN, we can have also binary black holes dynamically formed in accretion disks. So studying this in the context of host galaxies is very important also, because they can help us to identify the electromagnetic counterpart of gravitational wave events. Nowadays, with the sky localization, when they report one gravitational wave event, the sky localization is very, very large. And as you may heard, there is a huge effort in general to look for the electromagnetic counterpart of these events. So if we know within the sky localization for each event, which are the regions where or the host galaxies that are most likely to host one of these events, we can reduce the sky localization a lot. So for that reason, the host galaxy perspective is very important. And the third reason I like to talk about is because since gravitational waves are standard sirens, if we know information about the host galaxy plus the information that we can retrieve from the gravitational wave event, we can have an additional measurement of the Hubble constant. So yeah, this is something that is, well, it's not very recent, this paper, but there are many more recent papers discussing this. But even if we don't have an electromagnetic counterpart for each event, having some information of which are the most likely host galaxies, we can study and make some estimation for the Hubble constant. Okay. I wanted to mention also the one special case. For now, it's the only one with a host galaxy identified, because it's the only one where we have an electromagnetic counterpart detection, which is GW170817, which is the first binary neutron star merger detected by LIGO Virgo at the time. And well, the host galaxy is NGC 4993. It's a galaxy with a stellar mass in the range of 0.3 to 1.3 10 to the 11 solar masses. And one special particular property is that it's a kind of, well, early time and quiescent galaxy. And at that time, they were waiting that this kind of events of binary compact object mergers might be more likely to have them in star-forming galaxies. So there was a big question mark of why we are detecting the first electromagnetic counterpart in an early type quiescent galaxy. So if we have a tension in the model. So then at that time I started working on this aspect, so it was very timely. And so what we did was to combine the results from the Eagle simulation with stellar evolution models from MOPSI. So I am not showing here the details, but one can use the stellar particles from the cosmological simulations, combining this with the stellar evolution models, and create a merger rate per galaxy, the number of events per unit time for each galaxy. And this is what we did. So here on the top panel, you see the exactly that, the merger rate per galaxy and on the y-axis, and on the x-axis you have the stellar mass of the galaxies. And so each point represents a galaxy, and the color code represents the metallicity of the galaxy. So one of the results that we found that is very important is that there is a very strong correlation with the mass, where the massive galaxies have a higher merger rate per galaxy. So massive galaxies are the best place to look for merging binary compact objects. At least this is, I forgot to tell you, but this study was for galaxies in the local universe. Then we also explore a higher redshift, but I'm not focusing on this today. On the bottom panel, you see the star formation rate of the galaxies as a function of the stellar mass. And the color here is now the merger rate per galaxy. And the star, it represents NGC 4993. You remember the host galaxy of the first binary neutron star. And as you see, the merger rate per galaxy is higher in this region. So telling us that after all, this host galaxy, this first host galaxy, is placed where we expect to have many more events. So in principle, it's a likely place to identify an electromagnetic counterpart. We did this also like a full analysis of the total amount of stellar mass that we have in the local universe in early type galaxies, which is, we also estimated this from observations, this 70%. And yeah, we conclude that early type galaxies are likely places to detect, where I put DNS is double neutron star, or is the same that binary neutron star mergers at redshift 0. Okay, so then I wanted to show you a little bit more about, so this review from Tauri, which is very nice, about the isolated scenario. The isolated scenario is one of these channels where, okay, the binary stellar systems form in isolation. They are not formed dynamically. And of course, my plan is not to focus in each stage, just to show you that eventually in this evolutionary scenario, we find a stage where after forming the first, well, this is for binary neutron stars, but this can be also a black hole. So after some point, some time, we can have a compact object and a massive star. And if they are close enough, this can be a high mass X-ray binary. So which is, now you will see in the next slide, but it's, as you see, a massive star that is releasing material that is accreted by the compact object and emitting X-ray emission. And the point is that this, as you see, can be one of the intermediate stages up to the end of the merger of this binary compact object. So one question that one can do is, what is the link between, what are the properties for these progenitors to end as a merger? And yeah, so exactly that's what I was saying. So how many of these, because as I said, we have many formation channels, but at some point we expect that some of them could have this intermediate state. Okay, I mentioned this, but okay, just to remind you, high mass X-ray binaries are systems composed of a compact object and a massive star about 10 to the 8. So we expect again that this massive star end as a compact object, and eventually these two can end as a binary compact object merger. And they are these high mass X-ray binaries are associated with recent star formation. The emission is in this range of, or even higher, in fact. And yeah, they tend to, so there are observational results that claim that they tend to be, they are more luminous and tend to be more numerous in low metallicity environments. So, and here is one of my advertisements is about what Felipe is doing, Felipe Vivanco, who is here in the picture. He is here suffering, poor guy, because he decided, so I like a lot hiking and running in the mountain, and he told me, I want to go with you. And yeah, poor guy, we went to Heidelberg in May. Well, now he's in Padua, and yeah, well, he said, yeah, I want to go with you, and he was suffering a little bit. But yeah, he was happy, as you see. So what he's doing now is he's using illustrious TNG, and in particular TNG 50 and the Milky Way type galaxies of TNG 50. And he's combining these, again, the stellar particles that we can retrieve from each galaxy, simulated galaxy, with a stellar evolution model now from the code that is called 7. That is developed especially for people in Padua and in Trieste. So we can get, as you see, I hope you can see because the resolution maybe it's not the best, it's very small, the titles and everything, but we can get the population of high mass X-ray binaries for different metallicities, and also the evolution of the number of sources with respect to the formation time of the binary system to the time that it starts to emit X-rays emission. No? So we can, this is just the formula that where we convolve the information of the mass or the properties that we can get from the stellar evolution codes based on the metallicity. We also use the information of the formation time of the stellar particles, and after that we can get a population of galaxies in a population of high mass X-ray binaries in Milky Way type galaxies. So this is one example. This is one galaxy. The points here are stellar particles, and then if the points here are the high mass X-ray binaries. As some of you that you are in the lectures, you remember the particles are very large, so large in mass. So we can have more than one high mass X-ray binary per particle, but we can model this combining with or convolving with the stellar evolution models. And here the color code represents the metallicity of the stellar particles from the simulation. He also he can compute the X-ray luminosity in each particle. Here the color code is by age, and again this is by metallicity. So the gray points are all the stellar particles, and again the colors are the particles that are identified to have high mass X-ray binaries. And I want to check if, yeah, this is one of the preliminary results that he has. So what we have done so far is to compare the population that he can do with combining these population synthesis models, stellar evolution models with these Milky Way type galaxies with observational data. So here on the left you have the eccentricity as a function of period. The red, blue, and magenta are observational data from 2022, and the gray and black points are the simulated data. And so yeah, as you see, we are getting good results so far. And on the right panel, I am showing you the mass companion star as a function of the mass of the compact object. So the compact object that can be a neutron star here in this range, or a black hole in this part. Again, the points with colors are observations. And as one of the first impression that you can see is that we have many more high mass X-ray binaries with a neutron star than a black hole. I didn't put the numbers, forgot, but believe me, you see the points. I think it's clear. And this is what we expect from observational data. So now the next step for him will be to continue use these stellar evolution models to see what is the link between the high mass X-ray binaries and the binary compact object mergers, which is what he's doing right now. So to summarize this part, I am going very slow, is that, well, gravitational wave astrophysics just began, that we have different formation channels for these binary compact object mergers, that the cosmological simulations are very useful to study the host galaxy properties and to study the formation channels. I hope I convinced you that we have shown that massive galaxies are the best place to look for binary compact object mergers. But still, metallicity and star formation rate play a role, but minor with respect to the mass. And well, now the last comment I did now in the couple of slides is that now we can reproduce the population of high mass binaries in Milky Way type galaxies, and our next step is to study the link between high mass binaries and gravitational wave events, of course from the isolated scenario. And this is an advertisement. We are organizing a school especially for graduate students in November, together with Tomás, Andrade, Macarena Lagos, and I don't see the names there, but well, there are more. No, because this is invited. Sorry, I don't see well. But Jane, Paola, Tomás, Macarena, and I, we are organizing this meeting, and this is the invited courses. Sorry. And that are more on the gravitational wave data analysis, ring down, but also there will be some astrophysics using 7, the code that Felipe is using, but also Sara Rastello will talk about different formation channels from the dynamical perspective. So you are welcome to register. So in the next part, the second part of my talk is I would like to talk about also potpourri of what we have been doing. We have been doing in the perspective of protocluster clusters and galaxy tracers for protoclusters. So what are protoclusters? What is a protocluster? They are what we expect the progenitors of what we know now as massive clusters, full of quench galaxies. So they are not what is written here, pre-virialized, not virialized cosmic structures, and and they are very large. As you see here, this is a picture taken from Chiang 2017, and you see that they, as the time passes, they tend to collapse. But here, in this during the first stages of the universe, a huge amount of star formation happened in these protocluster regions. So the big question mark is what happened. How is the evolution of this structure to end as a very quench regions, quench galaxies, quench clusters? And another aspect is when one do this from the observational perspective, we see that these protocluster regions are formed or composed of very wide options of galaxies, a zoo of galaxies, a zoo of space oddities, as I wrote there, like submillimeter galaxies, AGN radio galaxies, even quiescent galaxies. And so what is next? What are the big questions for protocluster science? What we need is a complete characterization of the protocluster environment. How do different selection techniques compare? Because the way to identify them are different. Where are massive galaxies? How are all these different zoo of galaxies are located within protoclusters? How do the properties of protocluster galaxies compare with those in the field? And the other thing is how and when do protoclusters evolve to clusters? How this happens? And and for this, of course, it requires a combination of detailed individual studies and statistical analysis. So now, in our case, what we have been doing is focusing on 2 of these tracers, galaxy tracers of protoclusters. From one side is submillimeter galaxies, which as I read here, they are dust obscure and massive gas rich. They have an intense starburst activity. Some of them harbor AGNs, and we believe that they are precursors of massive elliptical galaxies in the local universe. And on the other hand, we have Lyman-alpha emitters, which are, well, they have a very strong Lyman-alpha emission of course, also is connected with star formation. They are low in mass, they are faint, and they are very abundant in the early universe. the point is that when one compares the properties in protocluster regions, it is not very clear if, so for Lyman-alpha emitters, I would say that it is very well established that they are good tracers of protocluster regions. But for the case of submillimeter, it's not clear. In this case, in this paper of Harikane 2019, I will not focus much, but this is the projected correlation function, and the red points are the cross correlation between LAEs and redshift submillimeter galaxies. Redshift, I forgot, is between 4 to 6 in redshift, the red submillimeter galaxies. And you see that there is a very strong correlation between them. Also, it's maybe more clear here with the red points that are these submillimeter galaxies with respect to the Lyman-alpha emitters that are placed in the overdense regions in here, like in the protocluster region. But as I said, while for the case of Lyman-alpha emitters, I believe is more established that they are good tracers. For submillimeter galaxies, the role as protocluster tracers is controversial, and there are some papers claiming that they are not good tracers. And here it's another example that I will skip now, but we can discuss later. So this is everything in the context of the Odin survey, and I started working also this because I was in the US, because for historical things in my life, I ended there, and I started working with these people that is very nice, and so they are observers, and they were needing some predictions for these observations. This the Odin survey briefly is so it's a survey using the DECAM on Blanco telescope, and they use 3 different narrowband filters to sample the peak epoch of the cluster formation, which is the 3 redshift that you can see here: 4.5, 3.1, and 2.4. And yeah, so they trace with these narrowband filters. They can identify Lyman-alpha emitters. They expect to detect 100,000 Lyman-alpha emitters, lot of comma progenitors, Virgo progenitors, and yeah, a lot of science we can do with this, of course. This is just an example of one of the preliminary results. That's the paper done by Vandana. It's a PhD student at Purdue University, and here, so you see it's the Cosmopila 3.1. You can see that the Lyman-alpha blobs, which are the stars, are linked with also close to prefer to live in Lyman-alpha emitter overdensities. But okay, and also this Odin survey is linked with a group of collaborators that belong to the Toltec. Again, I will briefly just mention that Toltec is still not working at this moment, but it will be released very soon. And so it has 3 wavelength bands, and the point is that with this Toltec survey, we will we expect to identify hundreds of submillimeter galaxies in the same fields than the Odin fields. So the plan, or our plan, is to combine the information that we retrieve from the Toltec survey with the camera that is Toltec, but the surveys has different names. But with these surveys that we can get with Toltec we expect to combine the information from Lyman-alpha emitter with submillimeter galaxies to study protocluster regions. Okay, so again, I said I work on hydrodynamical cosmological simulations. What did I do here? What we did was first to model a population of Lyman-alpha emitters in the cosmological simulations, in particular in illustrious TNG. Here you see an example. This is redshift 2 and a small piece of TNG 300 at redshift 2. And the points here represent our population of Lyman-alpha emitters. Here is the color code represents the luminosity. And the background is the dark matter distribution. So you see that we can study the distribution, the spatial distribution of these Lyman-alpha emitters. And what we did in particular so far was selecting a subset of massive clusters, identify a redshift 0 and track them back in time in this range, the massive cluster that we selected. And what we did was, having the population of Lyman-alpha emitters and the population of galaxies within these overdense regions that were tracked back in time, but first selected, as I said here, at redshift 0, we can use the history, the formation history, and study what is the evolution in terms of the star formation rate, the stellar mass, the halo mass, and specific star formation rate of the galaxies, and compare them with field. So as you see here, so what I am showing is, when it starts with C are the galaxies that belong to these protocluster regions. In the case LAE are the LAE galaxies, of course, and these are not LAE galaxies but belong to the same region. And one of the main results that we found is that, I will just focus especially here in this specific star formation rate, that with respect to the field galaxies, galaxies in protoclusters are much quenched, and they start quenching much faster than the field galaxies. And they also tend to live, but this is of course because of selection effect in massive halos at redshift 0. And yes, we found also some trends with the star formation rate and with the stellar mass. I forgot to mention, but this is work done by 2 undergraduate students at Purdue, and also by a postdoc at KIT, Moira and Tessa. Well, and we will submit this very soon. Now it's really under review of the Audi team, and we will release this soon. And the last thing I wanted to talk today is the modeling for submillimeter galaxies, which is very, very challenging, and is led by Ankit Kumar. The approach, so in this case, is very difficult because we need to account for the dust extinction in the case of submillimeter galaxies. For the dust is very important for this kind of galaxies. And since the resolution is in the case of TNG or the large boxes that are the best ones to study protocluster regions, because we have many more protoclusters and big overdense regions in the massive, in the large simulated boxes. Because of lack of resolution, one option is to implement the results obtained with fitting relations from radiative transfer results. Implement this so that we can extract from other works, and implement these fitting relations in poor resolution cosmological simulations, like in the case of Illustris TNG and Flamingo, that is what he did in particular, Ankit did. So we use this relation between the star formation rate of the galaxies, the dust mass, and we compute the number of counts here, and we compare this with the observational data. This L21 and H13 is because we are using 2 different approaches for this fitting relation. From Lovell and from Hayward are 2 different works with that they use radiative transfer results. And as you see, and this is something we were discussing this week also here, is that it's very hard for cosmological simulations to reproduce the observational data of number of counts. However, now we believe, or we think, or we found, to say, that with Flamingo we can start to reproduce a little bit better the number of counts. And this is good because Flamingo is a very large box. It's 1,000 megaparsec size box. So we have plenty of protoclusters. Yeah. Another thing that I wanted to show is this model with the distribution of submillimeter galaxies on the left panel. So as a function of redshift. The background in gray are observational data. And so you see here again different cosmological simulations. The red is Flamingo, the largest one. TNG 100 is the magenta, yellow is TNG, no, sorry, yeah, 100, 300 is yellowish. And you see that again we find that we can reproduce much better the distribution with redshift for the case of Flamingo. And on the right panel, here is a comparison of the cosmic star formation rate. Sorry, I forgot to say it, but again, these two different panels is because the model L21 and H13 from the previous slide. It's just the fitting values that we use. And the same here, top and bottom are different fitting values. And we compare again, the cosmic star formation rate are the dashed lines on the top and the bottom, and the field lines are for the case of the contribution from submillimeter galaxies. And what we found in particular is that around redshift 3, I would say, we find that the contribution to the star formation rate density is very high. It's about 30% when we make the ratio. I am not showing here, but it's very important if we use the data from Flamingo. But you see that there is a strong difference. At least now, again, with Flamingo, it seems that we start modeling well. And the last thing I wanted to show you is that there's a video that Ankit did with Flamingo. It's just to show that now, since we have this information for different redshift, our plan is, now that we have the way to model Lyman-alpha emitters, even when I show you for TNG so far, we are planning to implement a model of Lyman-alpha emitters in Flamingo, and we have submillimeter galaxies. So now our plan is to use Flamingo to study protocluster regions in Flamingo and compare the different populations like Lyman-alpha emitters with submillimeter galaxies and see what are the conditions for these two different tracers to trace protoclusters. So, I press this on. So this is my second summary to show that with cosmological hydrodynamical simulations we can be a good complement to study protocluster tracers like Lyman-alpha emitters and submillimeter galaxies. That one of the main results of this work that is almost done is that the protocluster galaxies, including LAEs, begin to quench much earlier at redshift between 0.8 to 1.6 than field galaxies. That this highlights the importance of large-scale environment in the formation history of galaxies. And then the last comment I did today was that Flamingo simulation shows reasonable good results for modeling submillimeter galaxies, and now our plan is to study the link between these two formation channel, two tracers of protocluster structures. And the last comment I had to do, because of course people at the university asked me to do that, is because we have open positions for PhD at the Universidad Bello. That the deadline is in a couple of days, but yeah, if someone is interested, you can also come and ask me if you have questions. That's all, and thank you very much.
Questions?
What makes Flamingo so good for the fitting of SMGs? Because this apparently doesn't happen with other simulations.
Yeah, this is something we are trying to understand what is the role, what's going on, why is the best model. I still don't understand, to be honest. There are some things, because one is that, for instance, the star formation rate is not that good. It's like we can model one thing, but not the other is. So I believe that this delay star formation, for some reason, is like it shifts everything from here to here, and then again creates more. Yeah, we can also reproduce number of counts with it, but yeah.
Just
sorry,
another.
I forgot to. Well, but you did the question with the microphone. I forgot that.
No, it's interesting because apparently, if you fit SMGs, you don't fit other things.
Yeah, exactly, exactly.
Yeah. What is the place where the Toltec camera is installed?
It's in Mexico. It's in.
Is it the super?
Yeah, it's
the submillimeter.
Yeah, in large millimeter telescope.
Ah, okay.
Yeah.
Okay, thank you.
Nice talk, Maria. Can you explain again how do you calculate the rate of the formation of the strong binary system, and why they are likely happening in early galaxies?
Yes, sure. So the way we do is the following. It's very similar to, at the end, to this that we do here for the high mass. So we have, let's say that we have a galaxy in the simulation, in the Eagle simulation in that case, and we have the mass of the particles, the metallicity of the particles, and the age. We use this information with catalogs from this population synthesis codes that we have a catalog of the number of sources, delay times, metallicity, etc., and we can convolve the information between the stellar particles in the galaxy catalog with the stellar evolution models. Okay, so let's say that we have a number of binary compact objects in a galaxy that we can create with this. We have the delay time. We know when they will merge. Okay, this is something that we do using the whole time, the Hubble time. Okay, so you can identify the particles in a galaxy at very high redshift, study the evolution, and since you have the delay time, you know when they are gonna merge. Okay, and then let's say that you stop and you take a picture of all the mergers in a bin of time, like in the local universe. So you know how many events happen in the local universe. And then, yes, since you have a bin, then you divide by time, and then you have the merger rate. This is like quickly speaking, but I hope it's clear.
Okay, thank you.
Luis Abramo?
There is a question.
Yeah, from Luis.
Yes, thank you. Hi, Celeste. Thanks for the talk. I wonder if the nice results you got for the Lyman-alpha emitters and submillimeter, if you thought about also the Lyman-alpha absorbers and the damp Lyman-alpha systems, which we are hoping to get from DESI and other surveys. So is this also something that we can reliably look for in the simulations, in particular Flamingo?
Yes, the model, of course, I didn't mention how we did, but for the case of Lyman-alpha emitters, what we did is, so there is a link, right, between the Lyman break galaxies and Lyman-alpha emitters with respect to the UV emission. So let's see if I understood your question, but what we are doing accounts for the transmission factor in the intergalactic medium and the transmission function of the intergalactic medium. And in that sense, we expect to have a reliable set of galaxies, set of Lyman-alpha emitters that can be compared with the observational data. I don't know if that answers your question, because
No, that's for sure. I was asking about the other side of this, the typically lower density, less virialized systems, which are typical that find in Lyman-alpha absorption, right? So
okay.
these are the other side of this. Well, I'm asking because you seem to reproduce better some systems which are relatively small compared to
Okay.
small in recently collapsed, and this is the case of the Lyman-alpha absorbers. So that's what I'm asking, if this is something that can be resolved better in the simulations that you're talking about now, especially Flamingo.
Yeah. Okay. Yeah. Okay. Now I understood. Yeah. We didn't discuss this because I'm not sure, again, because of resolution, right? Because the resolution is not good enough in Flamingo. In fact, the particles in Flamingo are of the order of 10 to the 8 solar masses, so they are very large. So I don't.
Okay.
I don't expect such kind
Yeah.
of,
In that case, it's probably very hard. All right.
Yes. Yeah. Exactly. Yeah.
Thank you.
Oh, thanks.
No more questions?
Hello, I'm interested in knowing about the first part, where you estimate the merger rates combining Illustris TNG and 7. How are these results dependent on the initial mass function? And to tell something about the fact, for example, the assumptions that you consider directly or indirectly in Illustris TNG might not be the same. The ones are considering a chemical evolution model, for example, 7. How to keep it under control? Is it an issue, or it's not relevant for your analysis?
For the initial mass function first. For the initial mass function, yes, in principle, one expects this might change for sure. We didn't explore that. There are other parameters we explore in the population synthesis code, like the, for instance, the percentage that of the mass that is accreted to the compact object, or the circularization. There are other free parameters in the population synthesis code that we explore, but not the initial mass function, to be honest. So I assume this, of course, will change the proportion of from black holes and neutron star systems. Yes. And in terms of chemical evolution, yes, also it's important to have this in mind. Of course, the good thing is that in principle TNG is doing much better than before with the chemical evolution of galaxies. So that's why we are still implementing the metallicity that comes from the stellar particles. Of course, so the benefit of doing this approach is also because we have the spatial resolution and we have good statistics to do this analysis. But of course, there are other approaches that can be done similarly, like maybe have a toy model for the Milky Way and explore and combine this with stellar evolution. Yes, but again, I would say that the benefit of this is the statistics, because you have a lot of statistics, and then you have good spatial resolution, so you can discuss other aspects. That's why we decided to go with it. This answered your question, more or less? Okay.
More questions? No? Thank you, Maria Celeste.
Thanks to you all.